Okay, so ions. Ion, remember, is a charged particle. So, metals, just remember, left of that stair-step line on the periodic table. They're going to lose electrons to get their noble gas electron configuration, and they form, I already found one typo, positive ions, which are called cations. Transition metals form more than one ion. That's why we use those Roman numerals in their names. And they're going to lose electrons in order to get a noble gas electron configuration. So, if we have CS right there, its electron configuration is 6s1. It's going to lose that one valence electron. Because when it does, we take xenon 6s1 and lose that electron configuration. All we have left is xenon. Now, it's going to become a +1 ion. Its formula is not going to be sodium. Its formula is going to be CS for the +1. And so its electron configuration is now this, which is the same as xenon. Now, if we have aluminum, neon 3s2 3p1, it's going to lose all of those valence electrons. So now it's got 13 protons, 10 electrons. That's why it has a +3 charge. And the electron configuration left is the same as that of neon. Now, nonmetals gain electrons, so they form negative ions, which we call anions. And again, to get a noble gas electron configuration. So, noble gases, remember, end with P6. So here's oxygen, ends with P4, so it's got to gain 2. So we have a -2 ion, and it ends with P6. Now bromine ends with P5, so it's going to gain 1 to get its P6, and so it's going to be a -1 ion compared to oxygen's -2. Now when ions come together in the solid phase, they're going to form crystals, as they're going to pack together to maximize the positive and negative attractions. So we would have this kind of thing going on, but in 3 dimensions. Compounds have to be neutral, but these are all empirical formulas, which means it's the lowest whole number ratio. And we crisscross charges. So if we had aluminum bromide, aluminum with its +3, bromide with its -1, we would have this, and there shouldn't be any space there. Now, the size of ions. Kind of hard to define these, so the patterns are important. Cations, smaller than the parent atom because they lose electrons. So let's look at sodium. Okay, it's got that 1 electron there, and the rest is all full. Now, We draw that again, and pretend these are identical. So that's all full, and we've got our valence electron there. In order to become the +1 ion, sodium has to lose that electron, which means that whole shell empties out. Oh, why won't it let me go back to the pen? So clearly, the atom is larger, the ion is smaller. So the anion is larger because of gaining electrons. So we have the same number of protons now trying to attract more electrons. Now, as long as we are comparing two pluses to each other or two minuses to each other, it's going to increase when it goes down to a column. When it goes down a column, because of more energy levels, and decrease going across a period because of increased nuclear charge. Now, isoelectronic atoms. Never see iso in a word, it means same. So these are ions containing the same number of electrons. So in this case, the one with more protons is the smallest, or is the smaller. So you can compare any ions that have the same noble gas electron configuration. The one with more protons will be smaller. The one with less protons will be larger.